There is a machine hidden inside a laboratory in California, surrounded by layers of technology designed to protect something so fragile that even the faintest contact with the outside world can destroy it. It is not dangerous. It does not contain an explosive core or a radioactive substance. But before we uncover what makes this machine so extraordinary, take a moment to subscribe to the channel and help us reach our goal of 1,000 subscribers. Your support helps us bring more stories like this to you. Its danger is something far stranger. Now, let's uncover what is really happening inside this mysterious machine. The machine has to be kept colder than deep space because inside it, something extraordinary is happening. The moment the outside world interferes with the quantum state within, that delicate state can begin to collapse. And that is where the story takes an unsettling turn, because this machine is not simply trying to calculate faster. It is allowing scientists to manipulate one of the deepest mysteries in physics. A mystery that asks a question humanity has struggled with for nearly a century. What does reality do before it is observed? Inside a quantum computer, the smallest components are not ordinary computer bits. They are called qubits. A conventional computer bit has a simple choice. It can be 0 or it can be 1. A qubit is different. Under the strange rules of quantum mechanics, it can exist in a superposition of both possibilities at the same time. For a brief moment, it is not forced to choose. And that strange ability is what gives quantum computers their potential. As more qubits become entangled, their quantum states can become connected in ways that have no simple classical equivalent. Together, they can represent and manipulate an enormous space of possibilities that a conventional computer would struggle to follow. But there is a terrifying weakness hidden inside this power. Superposition is incredibly fragile. A tiny vibration can interfere with it. A stray photon can disturb it. Even a microscopic electromagnetic fluctuation can destroy the delicate quantum state. The outside universe is constantly trying to interact with the machine. And that is why these computers must be cooled to temperatures colder than deep space. The engineers are essentially creating a tiny protected zone, isolating the qubits from as much of the surrounding universe as possible. For a brief moment, the machine creates a place where the normal interference of the universe is almost shut out. And inside that silence, something extraordinary can happen. The qubits can calculate while reality has not yet chosen a single answer. But this mystery did not begin with quantum computers. Long before machines like Google's Willow existed, physicists were already confronting the strange behavior of quantum particles. One of the most famous demonstrations came from an experiment that sounds almost impossibly simple: the double-slit experiment. Imagine sending particles toward a barrier containing two narrow openings. If you do not measure which opening each particle passes through, something astonishing happens. Instead of behaving like ordinary little objects, traveling along one definite path, the particles create an interference pattern. It looks as though each particle somehow behaves like a wave, passing through both slits at once. The possibilities overlap. The particle seems to exist in a strange combination of potential outcomes. But then the experiment changes. A detector is placed beside the slits. Its purpose is simple: find out which slit the particle actually used. And suddenly, the interference pattern disappears. The particle behaves as though it chose one path. That is the detail that has disturbed physicists for generations. The difference is not simply a collision. It is not merely a change in movement. It is information. When the universe has no record of which path was taken, the particle behaves like a wave of possibilities. But when information about the path becomes available, those possibilities disappear, and one definite outcome remains. Somehow, The act of information becoming available is connected to the transition from quantum possibilities to the classical reality we experience. And that leads directly back to the machine in California. Because inside a quantum computer, engineers are deliberately trying to prevent that transition from happening too soon. They are trying to keep the quantum possibilities alive. They are trying to hold open a door that the natural world normally closes almost instantly. And the deeper scientists go into this strange quantum world, the more disturbing the question becomes. If the universe allows multiple possibilities before measurement, then what exactly is reality before we observe it? Is the world we see the complete reality? Or is it only the final surface of something much stranger underneath? For decades, physicists have been able to predict quantum behavior with extraordinary accuracy. The mathematics works, the experiments work, the machines work. But beneath all of that success, one fundamental mystery remains. Why does one definite reality emerge from many possible ones? That question has never truly disappeared. And now, humanity is building machines powerful enough to manipulate the very quantum behavior that created the mystery in the first place. The strange thing is that these machines are not revealing that physics is broken. They are revealing just how strange physics actually is. And somewhere inside that frozen laboratory, a tiny quantum processor is giving scientists a fleeting glimpse into a world where reality has not yet completely decided what it is going to become. For a moment, the possibilities remain open. For a moment, the outside world is held at a distance. And for a moment, humanity gets to watch the hidden machinery of quantum reality before it becomes the ordinary world we know. That is what makes the technology so fascinating. And perhaps, more importantly, that is what makes it so disturbing. When the universe has no record of which path a particle took, something extraordinary happens. The particle behaves like a wave of possibilities. But the moment information about that path becomes known, those possibilities disappear. One result remains. One reality. This strange transition is at the heart of what physicists call the measurement problem. For nearly a century, scientists have become incredibly good at predicting what quantum systems will do. Their equations can describe the probabilities with astonishing precision. But there is still a question hiding beneath all those successful predictions. Why does one definite reality emerge from many possible ones? No equation has completely settled that mystery, and Albert Einstein was deeply uncomfortable with the idea. Einstein believed that particles should possess definite properties before anyone measured them. To him, the idea that reality could somehow become definite only when it was observed felt incomplete, almost unacceptable. He believed there had to be something deeper underneath quantum mechanics. Perhaps hidden information, perhaps some underlying layer of reality that determined what particles were actually doing before anyone looked. For Einstein, quantum mechanics might have been describing our knowledge of reality rather than reality itself. But then another physicist transformed that philosophical argument into something that could actually be tested. His name was John Bell. Bell asked a simple but profound question. If particles really carried hidden instructions determining their behavior, would those hidden instructions have to obey certain mathematical limits? The answer was yes, but quantum mechanics made a different prediction. According to quantum theory, entangled particles could produce correlations stronger than those limits allowed. If experiments could demonstrate those correlations, Einstein's classical picture of hidden properties would face a serious problem. Eventually, the experiments were performed. And again, the universe sided with quantum mechanics. Entangled particles produced correlations that were too strong to fit Einstein's classical explanation. The result suggested something deeply uncomfortable. At the most fundamental level, reality does not appear to be constructed the way ordinary human intuition tells us it should be. And that means this story is not really about strange particles inside laboratories. It is about the world around us, the solid floor beneath your feet, the walls surrounding you, the objects you can touch, the familiar reality that feels completely stable. All of it may emerge from rules that are anything but familiar. And then, this ancient mystery entered a new era. The quantum world moved from the pages of physics textbooks into the machines being built by humanity. One of the most important examples was Google's Willow processor. Willow showed that delicate quantum states were no longer merely laboratory curiosities. Engineers were beginning to control them on a serious scale. The processor contained 105 qubits, and researchers reported improvements in coherence and major progress in quantum error correction. The significance was not simply the number of qubits, it was the demonstration that quantum systems could become more stable as they grew. That is one of the critical steps toward building useful quantum computers. But then came the part that captured the world's attention. In a benchmark test, Willow completed a calculation in minutes that would take an unimaginable amount of time for a classical supercomputer. The result was extraordinary, but it did not prove the existence of parallel universes. It did not solve the measurement problem, and it certainly did not reveal what reality ultimately is. Instead, it made the old question even harder to ignore. If a quantum computer is genuinely using superposition and entanglement to explore an enormous space of possibilities, then what is actually happening inside the machine while it calculates? That is where the story becomes truly unsettling. Because scientists know the mathematics works, the machine works, the predictions work, but the deeper meaning remains unresolved. And perhaps that is the most disturbing thing quantum artificial intelligence has exposed. Humanity is beginning to build the future on top of a reality we can manipulate with incredible precision, while still not completely understanding what that reality actually means. And there is an even stranger part. Quantum behavior is not trapped inside laboratories. It is not hidden exclusively inside machines like Willow. The same underlying quantum rules are operating right now, everywhere around you. They are inside the atoms of your body. They are in the air surrounding you. They are in the light moving through the room. They are part of the very structure of the world you experience every second. Your hands feel solid because they are constantly interacting with everything around them. Photons, air molecules, heat, surfaces, vibrations. Countless interactions are happening around you at every moment. And those interactions are what help turn the strange possibilities of the quantum world into the stable, classical reality your senses recognize. The world feels solid. The world feels definite. The world feels obvious. But underneath that familiar surface, the quantum rules never stopped operating. And perhaps the most unsettling question is not whether quantum computers can eventually become powerful enough to change our world. It is whether, by building them, we are finally beginning to see the hidden machinery beneath the world we thought we already understood. Photons, air molecules, heat, surfaces, vibrations, and countless other interactions are constantly surrounding you. And together, all of these interactions force the strange quantum possibilities beneath reality to settle into the stable classical world you experience. That is why your hand never appears to you in a bizarre superposition. It is not because quantum physics suddenly disappears when objects become large. It is because the environment is constantly interacting with you. It is constantly carrying information about what is happening. It is constantly pushing quantum systems toward one ordinary-looking outcome. This process has a name: Decoherence. It helps explain why the world around you feels definite and predictable, even though its deepest foundation is quantum. But inside a quantum computer, engineers are trying to do almost the exact opposite. Instead of allowing the environment to interact freely with the quantum system, they try to protect a tiny piece of reality from those interactions. They isolate the qubits. They shield them. They cool them. They do everything possible to keep the outside universe from disturbing them long enough for the quantum possibilities to remain alive. And that changes the meaning of every successful quantum calculation. It is almost like holding open a door that nature normally slams shut almost instantly. For a brief moment, the quantum possibilities remain exposed. And during that moment, humanity is not simply using quantum physics. We are watching the hidden machinery beneath reality remain visible. But the truly disturbing part of quantum artificial intelligence is not simply that these machines may become incredibly powerful. It is not even that they could eventually outperform classical computers in ways that reshape technology. The deeper issue is what these machines are forcing us to confront. A question that once seemed like philosophical background noise is suddenly becoming impossible to ignore. What is a possibility before it becomes real? Quantum mechanics offers several possible answers, but none of them feels completely comfortable. One interpretation suggests that the wave function is simply a mathematical tool we use to predict what will happen. Another suggests that every possible outcome may actually occur, with reality branching into different worlds. And another proposes that particles possess definite positions, guided by something deeper and invisible, such as underlying waves. Each interpretation tells a different story about what reality might actually be. Yet there is an eerie problem. They can reproduce the same experimental predictions. The mathematics continues to work, even while the meaning behind that mathematics remains unresolved. That is an incredibly rare situation. Humanity has learned how to build machines that depend on superposition, entanglement, and decoherence. We can manipulate these strange quantum effects. We can protect them. We can measure them. We can build technology around them. And yet, we still do not completely agree on what they are telling us about reality itself. It is almost like discovering how to sail across an ocean before understanding what water really is. And perhaps that is why Willow feels so important. The machine did not answer the ancient question. It did something more unsettling. It made the question impossible to ignore. The machine works. The quantum state is real enough to protect. The computation is real enough to measure. But underneath it all, the deepest mystery remains open. When reality contains many possible paths, why do we experience only one? So, what did quantum artificial intelligence really expose about reality? Not that the universe is broken, not that physics has failed, but something far more unsettling. The world we experience as solid, stable, and obvious may only be the final surface of a much deeper quantum process. A process that is happening beneath everything, all the time. Every object around you may feel definite because the environment is constantly interacting with it, constantly recording information, and constantly forcing fragile possibilities to settle into the familiar reality your senses can understand. But when a quantum computer isolates its qubits from that environment, even for an incredibly short period, it gives us something we almost never get to see: reality before it fully becomes classical. And that is where the story becomes even stranger. Because perhaps the solid world we know is not the beginning of reality. Perhaps it is the result. The final layer that emerges after countless quantum possibilities have interacted with the environment and settled into the world we recognize. And somewhere inside a laboratory, a tiny processor is allowing scientists to hold that process open for just a little longer. long enough to glimpse what lies beneath the surface, long enough to make us wonder whether the reality we see every day is only one possible expression of something far deeper. And if that is true, then the greatest mystery may not be what quantum computers will eventually calculate. It may be what they reveal about the reality that makes calculation possible in the first place. Every object around you feels definite. The chair beneath you, the walls around you, your own hands. Everything appears solid because the environment is constantly interacting with it, constantly carrying information about it, and constantly forcing fragile quantum possibilities to settle into the familiar reality your senses can understand. But inside a quantum computer, engineers are attempting something completely different. They isolate the qubits from the surrounding environment. They protect them from interference. And even for a fraction of a millisecond, that isolation can reveal something we almost never get to see. Reality before it fully becomes classical. That is why machines like Willow are so important. They are not simply faster computers. They are controlled cracks in the wall between the world we experience and the quantum world beneath it. For nearly a century, physicists have known that particles can behave like waves of possibility. They have watched entangled systems remain connected in ways that defy ordinary intuition. And they have seen measurement somehow turn many possible outcomes into one result that we experience as reality. But for most of that history, these questions were debated on chalkboards, inside laboratories, and across the pages of physics textbooks. Now, something has changed. Humanity is building machines that depend on those very mysteries. This is the strange new era we are entering. We can engineer superposition. We can protect entanglement. We can reduce quantum errors. And we can make machines calculate using rules that still challenge our deepest understanding of what reality actually is. And yet, after all these advances, the central question remains unanswered. When the quantum world contains many possible paths, why do we experience only this one? Maybe the answer is collapse. Maybe the answer is branching worlds. Maybe the answer lies inside some deeper layer of physics that humanity has not discovered yet. We simply do not know. But whatever the ultimate answer turns out to be, quantum artificial intelligence has made one thing impossible to ignore. Reality is not as simple as it looks. The classical world may be the version of reality we are capable of experiencing, the version we can survive inside, but it may not be the complete story. Beneath every solid object, every breath, every beam of light, and every atom inside your body, there is a quantum foundation, a place where possibility is not imagination. Possibility is structure. And somewhere inside a laboratory surrounded by extraordinary cooling systems and technology designed to isolate it from the outside world, a tiny quantum chip is holding that foundation open for a fleeting moment, just long enough for humanity to ask one of the most dangerous questions in science.